Recording started.
Good morning, you guys. I hope you're doing well today. As I stated in the chat bar, the Olympics start today. Woohoo! I'm totally an Olympic fan. I'm not athletic at all, so I have to live my dreams through other people, aka the television and the Olympics every 2 years. So whether it's winter or summer, every 2 years I'm glued to the TV for about 2 weeks straight whenever they're on. So they start tonight. Woohoo! I think ice skating is on tonight. Yay! And then the opening ceremony is tomorrow. So if you need me, you'll find me on my couch tomorrow night. All right, I digress though, because I guess you guys don't have the same feeling about the Olympics that I do. All right, today we are going to be looking at 6.05, which is on more graphs of our polar equations. So in Tuesday's class, and this week seems to be going really slow for some reason. I woke up this morning thinking it was Friday, so little discouraged that I found out it was only Thursday, but I get to see you guys, so that was good. Um, but Tuesday, we talked about our polar equations. The assignments that came in looked great. There's maybe like one mistake here or there, but nothing like that everybody got wrong. So I don't see any like collective like concept that I need to kind of fix or anything. I know, right, Isaiah? That's kind of what I had in my mind. Like, it's Friday, woohoo! Oh, nope, it's only Thursday. I'm a whole day ahead of myself. Are there any major questions that you guys had for me? Because I don't want to cut you guys off early if there are. If there are no major questions regarding 6.04, then we'll go ahead and move forward into 6.05, which is looking at more graphs of our polar equations. No, I know, right? Life doesn't skip a quiz. I wish it would, though. Once in a while, I wish it would just throw me a bone, but nope, we're not that lucky. All right, then if there are no questions with your polar equations, we're going to continue moving forward. I think you'll like today's lesson. I don't think it's quite um, as straining as some of the past ones have been. So if there's just a few like maybe formulas that we got to jot down, and once we have those, I think we'll be good to go. And we will need a graphing calculator since we're looking at graphs of polar equations. It'll be helpful to actually graph them and see them as well. So if we have that graphing calculator, it'll come in useful from time to time. If you don't have that graphing calculator, using the Desmos one will work just as well. All right, so the first thing we're going to talk about before we get to all the different type of graphs of polar equations we can run into is the symmetry behind them. So most of our polar equations have some sort of symmetry going on. There are three types of symmetry that we can look for or test for. The first type is through the x-axis. Now, they don't call it the x-axis, they call it the polar axis. But if you hear that term polar axis, note that you're really testing based off of the x-axis there. So is there symmetry about the x-axis? So as you can see in graph A here, it is symmetric about the x-axis because if I take a look at that x-axis, the graph is kind of reflected right over that. So there is symmetry there. To test algebraically, if you didn't have the graph of that function or equation, you can go ahead and test by replacing r and theta with r and negative theta and then simplifying. If you are able to simplify your equation back to the original, then you know that it's symmetric about the x-axis. Now to test for the y-axis, and they don't necessarily call that the y-axis when you're working in your polar mode. So instead of the y-axis, they refer to that as the line theta equals pi over 2. And hopefully that makes sense, because if you're looking at your unit circle, pi over 2 is the one that just goes straight up and down, right? So you may hear that referred to as pi, the line of pi over 2 instead of your y-axis. But the y-axis is what we're more familiar with. Okay. So that example right there, we can test for symmetry algebraically by replacing r theta in your equation with negative r and negative theta, and then simplifying that. If you're able to simplify the equation back to the original, then you know it's symmetric about the y-axis. And then the last symmetry is your origin, which they refer to as the pole when we're talking about the polar mode. So the origin right here is obviously just the center graph, or the center point right in the middle. To test that, we replace r theta with negative r theta, and then we try to simplify. They give you alternate forms you can replace it with, but you would need more properties and identities if you're going to use these second forms instead of just the first ones. We may even need some properties to help us simplify using just these first set of order pairs. The first set is what we're going to stick to algebraically to show symmetry. I'm not going to refer to these sets of points at all today. All right, so 3 things that we're looking out for as far as symmetry goes. When we get into specific types of polar equations, like the graphs of polar equations, we'll be able to identify the symmetry a little bit more easily, I guess that's a term, because they'll give us actual rules that will identify. Besides using the simplification process, there's other rules that can pinpoint what type of symmetry is going to occur. So that's good news, is that we don't always have to use this simplification process. There might be other things that lead us to the symmetry as well. Okay. All right. So let's go ahead and actually test for symmetry here, and I threw up the symmetry test that I had on the last slide, so if you're still copying that down, it's right here, your symmetry test for your polar graphs. And then I also pulled some identities that I think might be useful when we're trying to simplify after we substitute in. So I do think that these 2 boxes here, the odd-even identities and the cofunction identities, might be useful to you when you're working through the exercises in the book, or when you get to the homework in Canvas. You might want to rely on those couple of functions or identities to help you simplify somewhere. All right, so the first one says use the appropriate symmetry test to prove that r equals 4 sine 3 theta is symmetric about the y-axis. So if we're trying to prove about the y-axis, that's kind of nice that they told us what symmetry we should be testing. They might not do that. If they don't tell you what symmetry to test for, you have to look at all 3, and you have to do all 3 substitutions and simplifications. Okay? We're lucky enough in this first example that they narrow it down and tell us just to test the y-axis. But again, we might not always be that lucky, and we may have to test all 3 to see what it's actually symmetric about. Okay, so just heads up on that. So if we're testing about that y-axis, I'm going to substitute in negative r, negative theta into my equation. So we're going to go ahead, and that's going to be a negative r equals 4 times sine of 3 times negative theta. All right, let's see if we can simplify this. And technically, the first thing that I would try to do is work inside the parentheses here. Well, 3 times negative theta, I can take the 3 out, and I think I can take, well, I don't think I need to take the 3 out. I can move the negative sign in front of that, right? So technically, inside parentheses there, I think we're all comfortable with knowing that we can go ahead and rewrite it like that, right? We can just kind of put that negative sign out in front since it's multiplying 3 times negative 1, right? Everyone's good with that? Okay, then I'm probably going to have to use up above here the even-odd identity to simplify the next step. I see that sign of a negative number inside the parentheses equals negative sign of the number. So I believe I can just pull the negative out in front. So if I pull the negative out in front of my sign, and 3 theta is the same as the x in this case, then I'm just left with that 3 theta. So here is where I use the odd even identity up above to help me simplify to the next step. Any questions from how we got from here down to here using this odd even identity up from above? All right, then what's my last step, you think? Remember, we're trying to get back to the original. Divide by negative 1. Yep, if you can divide both sides by negative 1, let's see, you are back to your original, right? Or multiply by a negative 1. Yep, that works too. But either way you look at it, you're back to your original. And that's what we needed to get to, right? We wanted to get back to that original equation to show the symmetry was present. So because we were able to simplify in those couple of steps there and get back to the original, this does have symmetry about the y-axis. Your brain must be wired differently, Isaias. No, I'm just kidding. Maybe when you were in algebra and you were solving for your variable, maybe your teacher at the time just decided to use multiplication versus division. It could be just something as simple as that. The good news is that you're doing it correctly either way, so that's what counts. Any questions with that first one? Probably. So again, I just pulled these from the book. I think they were in like 6.01 or 6.02 lesson. So from the way beginning of the unit, I want to say, is where I took these from. So if you need them, just remember, go back and take them from there. But they will help you immensely with that simplification process. So if you get stuck with the simplifying, look towards one of these identities to help you move forward. Okay, now on to more about our graphs. So when we graph our polar equations, usually they tell us like what type of window to look in, right? So whether it's from negative 10 to positive 10 or whatnot. Knowing the maximum value of our graphs, because most of our polar equations are bounded. They're like circles or flowers or cardioids of some sort, but most of the shapes are bounded, meaning there is a beginning and an end, a high point and a low point, right? So if we can figure out what the maximum point is to our graph, it's going to help us find the correct viewing window to look in instead of having to make a bunch of adjustments until we can finally see it as a whole picture. So the next thing we're going to look at is how we can find the maximum value for R, which will help us then determine the viewing window we might need when we go to graph the actual equation. All right, so to find the maximum value for R, we first take a look at our function that's given here, or our trig function. So cosine theta, and we always take if it's theta or 2 theta or 3 theta, we always kind of group that together. But according to our unit circle, what is the maximum and minimum values for x for cosine? So looking at the maximum and minimum values for x on the unit circle for cosine, what are those numbers? Think of your radius. So when you go and you look at the unit circle, what's the maximum and minimum value that you can get? 1 and -1. Yep, so we're going to just kind of start with that basic. And now we're going to tweak these numbers based on what the rest of our equation is. So the first thing we're going to do is I have 2 times cosine in my equation. So 2 times means I'm going to multiply everything by 2 in this setup. So we'll get a -2 is less than or equal to 2 times cosine theta is less than or equal to 2. All right, the next piece of our equation is adding 2, right? So if I add 2 to everything, let's see how this adjusts my max and min values. -2 plus 2 is 0. I'll just add 2 to the middle. And then 2 plus 2 is 4 on this end. Now we've just went from our basic cosine function to our polar equation that was listed up above. So that means the graph itself will go from 0 to 4. So 4 is that maximum R value. So finding the maximum R value to find an appropriate viewing window, R would be 4 because that's the larger number there. All right, questions with how we did that process? So it was a little bit strange, but hopefully now that we saw it worked through, we were able to kind of follow along how we got to the 0, 4 there. Let's see if, I think I have another one. Let's see if we can do the same thing with this second example. So we're trying to find another maximum R value. So I'm taking a look at my equation right here, and I'm starting with just the trig part of it. So the middle, or the trig part of it right here, is the cosine 2 theta. Now, if you have a number in front of theta, it doesn't change your starting and end values on your unit circle. So that's the good news. So if you have something in front of that theta or connected to the theta here, it's not going to change your maximum and minimum starting values of -1 and +1. All right, same with the sine. If this were sine, you'd still use the same thing there. All right, now let's see how we have to adjust our graph to get our function. So what do we need to do in order to create our equation that we were given? We've got to multiply everything by 3. Yep. If I multiply everything by 3, that turns into a -3 is less than or equal to 3 cosine of 2 theta is less than or equal to 3. All right, and now we notice that we have in the middle here our equation that we were given. We can stop. What is the maximum R value of this polar equation? 3. Yep, because that is your ending number over here. So the maximum R value for that one, and I'm going to put that inside absolute values, is 3. Because we put the absolute value there for that -3 instance as well. And technically I could have done that over here. So the maximum R, I probably should have put this inside like the absolute value brackets, just so I can have my notation correctly. Okay, questions with that? I don't have to add 3 because there's no +3 up here. We had to multiply because that's the operation between the 3 and the cosine. Yeah, so I only added, if I go back here, I only added 2 after I multiplied because there was a +2 out at the start right here. So notice that kind of extra +2 there. The multiplying by 2 came in from this piece in green. So if I try to color code it, there's the green step, and here is the orange step. So this first equation had 2 pieces to it, kind of 2 steps you needed to do. This one over here only had the 1 step because we only had the multiplying by 3 in that equation that needed to be done. Yeah, so that was a good question. Any other questions regarding these? All right, here comes the fun stuff. So now we're going to start talking about the different specific types of graphs, the more common ones that we can run into with our polar equations. So the first one is what we call a rose curve. So a rose curve looks like a flower, right? Hence the rose name. And your rose curves can have a different amount of petals. So each little piece over here obviously is what we call a petal. You'll notice that in your box here, your petals are denoted with N. All right, so if N is odd, you have N number of petals. If N is even in your equation, you have 2 times N number of petals. So the number of petals that appear in your rose curve really rely on that N. So here, first of all, we're going to go back to the beginning because that's a good place to start. And your rose curves will fit these 2 formulas right here. So R equals A times cosine of n theta, or R equals A times sine of n theta. And n has to be greater than 1, right? So they do have that restriction for n as well. Can't be negative, can't be 0. So it's got to be an integer value greater than 1. All right, for your rose curves, every rose curve will have a domain of all real numbers, so negative infinity to positive infinity. And they will all have a range from -a to +a. So whatever the number is out front, that is going to kind of be your minimum and maximum values for the range. Okay, so that's what that means right there. It is continuous, meaning that you can draw the curve without having to pick up your pencil. There's no holes or breaks anywhere. There is symmetry for some of these rose curves. If n is even, so right here, whatever's in front of theta, if that's an even number, you know the rose curve will be symmetric about the x-axis, the y-axis, and the origin. Okay, so usually those are kind of more appealing to the eye because they have more symmetry there. If n is odd, so 3, 5, 7, because remember it can't be 1, it's got to be greater than 1. So we're looking at like 3, 5, 7, 9, 11, so forth. So if n is odd, then we know, and it's a cosine function, it's only symmetric about the x-axis. If it's odd and the sine function, then it's only symmetric about the y-axis. So it's going to be kind of more tilted appropriately, so it's symmetric about only one of those axes. Every rose curve is bounded, right? Makes sense because it's a flower, kind of a circular. It's not going to extend out into infinity somewhere. Your maximum value can be found by taking A or looking at A. There are no asymptotes. And then, like I had mentioned before, you can determine the number of petals based on the n or 2n there. So let's go ahead and analyze the graph here for the rose curve of r equals 3 times sine of 4 theta. Anytime you're asked to analyze a graph, it means you're asked to find all of these pieces that are listed above. Okay, so you would need to start with your domain. And a lot of these you're just kind of copying from the charts, right? So domain is all real numbers. Your range, what's the range for this first example? So if I'm taking a look at A, what is the value for A? 3, right? It's that number out in front. So it looks like we want -3 to +3 for the range. Yep. We'll say it's continuous. What about symmetry? What are we looking at here? First of all, we have to determine R or N. Is N even or odd? It's even. So if it's even, we know that it's symmetric about the x-axis, everything, yep, the y-axis, and the origin, so everything. We know it's bounded. What is the maximum R value? Yeah, we already know what it is that we did A before with the range, right? So 3, it should be that maximum of your range, which is our 3. No asymptotes. And then how many petals? So again, we're looking at n. Yep, n was even because it was a 4. So if it's even, we do 2 times n, so 2 times 4 is an 8. So you have 8 petals in your rose curve, and we can count them over here, and we do. So if you're asked to analyze a graph, first of all, there should be a chart for you to kind of follow and walk through like they have with the rose curves here. But that's exactly what you need to state, everything that they list in that chart. That's what they mean by analyze. So there's a lot of components to it, but if you have that chart available, you can just use it as a guide and go through it pretty quickly. Questions with the rose curves there at all? All right, the next one is our limacon curves. Woohoo! These look like cardioids almost because they kind of look like a heart, it reminds me of, but they're called our limacon curves. They are formed when we have an equation similar to these formats right here. So A plus or minus B times sine theta, and R equals A plus or minus B times cosine of theta. Now you will have a number out in front, so A has got to be greater than 0. You should be adding some value to your equation. And B also has to be greater than 0, so you need to have a number out in front of your sine and cosine. If you have that present, then you would want to follow these characteristics right here. Okay, note the symmetry depends on what type of trig value you have in your equation. If you're dealing with sine, it's symmetric about the y-axis. If you're dealing with cosine, it's symmetric about the x. To find the maximum r value, you're going to be taking a plus b. Okay, it doesn't matter the sign in the middle because it could be plus or minus. You simply are just taking the front number plus the number in front of your sine or cosine, and you want to add them together. Same thing when you're finding the range. You'll subtract and then add to find those. There are 4 different types of Limacon curves you can run into. You can see them here. You can get an inner loop. A cardioid, I said, is one of those because it looks like a heart. Pretty heart. A dimpled Limacon, it looks like a cardioid, but it's not as, the little bend in here is not as severe or sharp, I guess we could call it, as you have with the cardioid. And then this one's starting to look a little bit more like a circle, but it still has kind of a flatter piece on one side and is not a perfect circle quite yet. So this convex one at the end is starting to take the shape more of a circle, but it's not quite there yet. You do have some flatter pieces that are there. All right, let's go ahead and take a look at an example. You'll notice that I grabbed that chart so that we can analyze the graph here. So to analyze it, the first thing we need to start with is the domain. So we can see that that's all real numbers, right? Because it's negative infinity to positive infinity. What's my range going to be? Let's figure out the range. Zero to 6, yeah, because in my example here, A is 3 and B is 3, right? Because this is the A and this is the value for B. So 3 minus 3 is 0, 3 plus 3 is 6. So that's where Tommy got her values from. Good. It's continuous, which means that you can draw the graph without having to pick up the pencil at all. There's no holes or breaks or anything in it. There should be symmetry. What type of symmetry do we have in this Limacon graph? The y, because we're dealing with a sine function there, right? The sine there, and sine is symmetric about the y-axis. Good. Obviously, it's bounded. What's our maximum r value? Yep, that can also be found looking at your range, right? So that's going to be the high point of your range, which was our 6, because 3 plus 3 was 6, and there's no asymptotes. Oopsie, not asymptotes. Asymptotes. There we go. All right, so again, when we had that chart, really easy just to pull and substitute our values into the appropriate places. Questions with your Limacon curves at all? Yeah, I think I created a new vocabulary term there, huh? All right, it looks like I have another one here, so I just pulled the same chart. And this is what I would do if I were you and working through the book. I don't expect you to memorize these by any means, so constantly knowing which chart you're looking at is going to be key. So you should be able to identify, if they don't tell you what type of curve it is, you should be able to identify what chart you need based off of the equation itself. If you've got a plus or minus with some number, that's going to be a good indicator. You need to look at that Limacon curve, right? Because that's the only one that has the plus or minus out in front of it. if you have a number attached to the theta, that's going to be a good idea or a good indicator that maybe you have a Rose curve going on. So knowing and looking at the equation itself is going to be key to know what type of chart you're going to need. Okay, now that I'm going through here, let's start. Obviously, domain, we know. What's the range going to be for this one? Chances are that you'll probably have it memorized anyway. You work with it so much that it just becomes second nature. So even though I'm not expecting you to memorize it, I'm guessing that most of you probably will. Or at least have a good indicator of what you're looking for each time. All right, so continuous. Symmetry, where's my symmetry? Yeah, we're dealing with cosine this time. So that looks like it's going to be around the x-axis. And then the last thing is our maximum R. And I obviously want to state no asymptotes as well. Good. Questions with that? If we want to go ahead, we could graph it to C. I know we're getting to that point here pretty quickly. I'm nearing the end here. If you want to go ahead and graph this, I think you guys are still in polar mode. I have to change because I had to get out of polar mode. But 2 plus 3 cosine theta. I'm going to change my window. I'm going to do 0 to 5. We'll try 0 to 5. There we go. I'm like, I can't get it. Mine fell a little short. I think I have to change my viewing window or my T-step a little bit, but it looks like I definitely have a Limacon with an inner loop happening there at some point. I probably have to go to that online one I sent you guys, or Desmos, to get the full better graph of that. But hopefully your calculators are working a little bit better than mine. But I can see that it definitely is going to be a Limacon with an inner loop happening. All right, here are some other ones that aren't quite as popular as the Limacons and the Rose curves, but we can get a lemniscate curve. And that's going to be, obviously we have r squared and then a squared. And then your 2 times theta. So if you have any squareds, you know that you have a lemniscate curve happening, which looks like an infinity symbol, basically. So you have all of these things over here as far as the characteristics goes if you need to analyze that. Okay. Another type of one is the spiral of Archimedes. That's kind of cool, right? It's like you're hypnotized here. Keeps going on and on and on. You can tell that the spiral can change a little bit direction, so of where it starts. That spiral goes this way. This one's going this way. But that again looks like just r equaling theta. If we were to do that, you get your spiral of Archimedes. Again, you have all your characteristics here of your graph. Really, there's not much to go off with your spiral here because you have all real numbers for domain and range, continuous, no symmetry obviously. It's not bounded, keeps going on forever, which means there's no maximum value and no asymptote. So this one's kind of easy to analyze when you have it but still cool that we can get it off of a polar equation. All right, so this is what I want to wrap up with for today, is we're going to take a look at 9 through 12 from the textbook, and we're going to see if we can determine, first of all, which equation is graphed from up above, and then how do we know that. So it looks like we're dealing with our Limacon curves here. So first of all, let's see if we can identify if we're looking at sine or cosine example from up above. And you can either use the chart to help you analyze, or you can use your graphing calculator. So if you like to graph both of these and see which one of them appears, you can go ahead and do so, or you can use your characteristics to help you determine which one. I'm going to give you a moment to either work with your calculator and graph them, or work with your characteristics here, but then let's decide, is it the sine function or is it the cosine function, and which graph is it going to match up to up above. So when you think you have an answer, go ahead and throw it in the chat box. All right, so we're thinking it's the 2 minus 2 cosine theta. Anybody else agree with the 2 minus 2 cosine theta? And she says possibly graph C. Rachel also says 2 minus 2 cosine theta. I got a different graph that it matches up to, but you know, my calculator is a little bit picky sometimes. I didn't get it matching up to graph C. What do we get that to match up to? B. Yeah, I get it to match up to graph B. Here is when I did that. Here's mine. Obviously, we can change the viewing window to what they have up above. But I do see it kind of tilting to the left there. All right, another one we could have used if we're looking at our characteristics here, if you're going with cosine, that means it's symmetric about the x-axis. So symmetric about the x-axis means it has to be either B or C. The other two are symmetric about the y-axis. So we did have it narrowed down to either B or C. And then I guess you're looking at the maximum values there. So A plus B, well, it would have been 4 in either one. But it does look like this one is going out towards the left-hand side versus the right when we do finally graph it. Good question. Let's see. When the range is from 0 to 4, a minus b, 2 minus 2 is 0. Yeah, and 2 plus 2 is 4. I'm not quite sure how they're looking at that as far as the range goes with their Limacon curves. Because technically it would just be the bottom half of your graph then. I'm not quite sure how they would go off of the range either, looking at that. Right, exactly. I'm not quite, I don't know how that would come to be either. So I'll have to look into that a little bit more on how we get the range there with the a minus b and the a plus b. Okay, let's rely on our graphing calculator for the rest of these. For part B here, or question B, we have to decide, are we looking, cosine or cosine? So if it's cosine or cosine, that means we're looking for symmetry about the x-axis again. So the only other option we have is C for that, right? So if you're looking at the cosine, it's got to match up to C. So which one of these is going to match up to graph C? Is it the plus or the minus? Rachel's vote is for the plus. What's everybody else thinking? Mine too. And the range matches up for that one, right? 0 to 5. Or -1. -1 to 5. Sorry. So that one makes sense. -1 out to 5. I'm not sure what happened with the first one. How about 11? So we've only got symmetry with respect to the y-axis left. So with respect to the y-axis means it has to be sine. So obviously we're going to be going with this one right here. But which graph does that match up with? Part A or part D? And they're very, very close to each other. There's not much difference. Oh, you're right. I might have been looking at the wrong one before. Sorry, yeah, you're right. No, range is usually the y-axis. Which is maybe why I'm thinking differently, because maybe these are graphed in polar and not like rectangular. So maybe that's my issue. Is if it's graphing in polar mode and not rectangular, maybe things are matching up okay. And I'm thinking of rectangular coordinates versus polar coordinates. So that could be my problem there with why things aren't matching up the way they are. Algebraically, at least. All right, do we decide, is this A or D? Anybody just graph A? So Rachel's got graph A. Anybody else second that? I'm going to second that. I also got graph A for that one. And then the last one, obviously is going to match up to graph D. And again, that is symmetric about the y-axis. So if we have some symmetry about the y-axis, that's got to be your sine function. So we want to choose that sine equation instead. Okay, so definitely we'll probably need our calculators to help us through any of the graphing pieces. I'm wondering if we were to use that rule that we did at the very start with our sine and cosine being between -1 and 1, if that would help us at all or not determine our graphs. So maybe using that tactic can help us narrow down the choices as well. You know, like we did with the first couple examples, that might be able to help us distinguish which one's a better choice or not too. So just something else to try. But I know we're out of time here today, so we can kind of do that on our own before next week if we want to. But give the lesson a go. I think that you'll like it. Have these graphs or these charts available for analyzing any equations. If that pops up, you'll be able just to kind of copy and substitute the values in. Any major questions before I let you go today? Okay. Great. Then that's all I got for you. So we got one more lesson, I think, in the unit before we wrap it up next week. But we can start with any major questions that you guys ran into on Tuesday regarding your polar graphs. All right. Have a great day, everybody, and I'll see you again next week. Bye.